And
so,
go ahead, please.
Grimm, that's all about me. In the last 5 years, I played a lot with the new multi-threading functionality of C++ OX, C++11, and you know, I made a lot of mistakes. And these mistakes I will show you. This talk is special for me, maybe also for you. What's special about this talk is I will make it interactively. So in case you give me not answer, you will sit here for hours. So I hope. I will have a look here. I will walk with you to the functionality of C++11, and I will show to each topic a problem, and we discuss it. I will give a short context, and then we go to the code, which is mostly broken, and we discuss the solution. And I hope, so that's my hope, I will present you the solution. So, the first one, we talk about threads. What are threads? Threads need a work package and run immediately. You know it. The creator has to take care of his child, and he can do it in 2 ways. At first, he has to wait for his child, or he can detach himself from his child. That makes me think about my daughter, because she's become today 17. So you have to take care of your child. The thread has to accept the data by copy or by reference. That's the context. What's broken with this code? I think that's the extremely simple one. The more difficult one will come in the next slides. Any guess?
Wait.
You can.
You do not wait for the thread to complete, so you exit out of main, and you do not detach and
I don't
do
care
chain.
about my child. That's the point. I have to join it, so I have to wait for the child, or I have to detach it. Actually, what will happen? You will see here. You see, it's extremely interactive. That will happen because in case the thread T go out of scope, the destructor will be invoked, and there was no join taking place, so std terminate was invoked, and you see the result here. What should you do? You know, I give you the answer. You know it from before. You can join the thread, or you can detach it. Why is detach a bad idea in this case? Because it's thread, it must have a reason. I use the thread for a reason, you know? Why is detach a bad idea?
There's a data race between the output operation and the destruction of the cout object in the main thread.
You have no guarantee that the child thread will live long enough. So it's undefined behavior. So don't use detach in such case. Is it possible? No, not in such case. Though, one step further, to make this automatically joining possible, Anthony Williams, who wrote the book C++ Concurrency in Action, I can do it here, wrote a so-called scoped thread. Have a look here. This scoped thread accepts a thread, sets the thread, sets the work package of the thread, sets the stuff the thread wants to execute, and what he is doing is, in the destructor, he invokes tjoin. So he's done. So you cannot forget your thread. And yeah, that's all about it. That's the scoped thread from Scott Williams. Now, I will explain you in a few words this program, and then we will look at the consequences. Here I have a wall sleeper. That's only a value of initially 1,000. I give out the value. Then I invoke a thread, which will execute this work package, which is under the hood a function object. I additionally provide an argument 5. Then I detach the thread. Now have a look what my sleeper will do. My sleeper get E, that is actually wall sleeper by reference. You see it here and you see it here. Then that's the work the thread is actually doing. He sleeps, at first he iterates 6 times, sleeps for a short period of time, about 100 milliseconds, and then he adds K to E. E is taken by reference, and the thread is detached. What's wrong with this example? Good.
Multiple things. First of all, you detach instead of join, and then you have a data rise on the reference of I. It should be an atomic or something.
That's the point. But what's the key point here is what should be the value of wall sleeper here? If you can calculate 6 times 5, it should be 1030. You know, 6 times 5 adding to 1000 is 1030. We expect 1030. What's actually happening, now you see, what he said is you get 1000. Because the child time has not enough time to complete his work, and so you get only 1000 instead of 1030. What is the solution? I think that's obvious. Instead of detaching the thread, you join them. So the creator will wait for his child, and now the behavior is well defined. 1030. Only simple examples. In case you are bored, it will become more difficult. Now you know shared variables is a key point of multithreading. You can deal with this in 3 ways. I only show you 2 ones. You can have something like an atomic variable. You can have something like a mutex, or you can work with fences, which I will not deal with here. So, what's the problem here? I like it because it makes it extremely obvious. I show it here. I have here my main program. The boss says to all his workers, and you know this, guys. The boss says to all his workers, let's start working. Then thread help starts his work. Andre, Scott, Björn, Andre, David. Then after all threads are done, the boss, because he listens to his workers, he says, let's go home. So, one boss, a lot of workers. Have a look what the workers will do. They get their name. They iterate from 1 to 3. They sleep for a short period of time. And they shout, name, work, 1, 2, 3, done. That's their job. One point about sleeping. With sleeping, you can enforce the multi-threading problems. So I play a lot with sleeping for 1 millisecond, sleeping for 20 milliseconds. Though you see a dead race, so you see a critical a data race or something like that. That's the reason why I always play a little bit with time. What's the problem with this code? Here, you can say to me, I will repeat it.
You have a race on the shared resource cout.
Yeah, of course. Cout is a global variable. That one you have to protect. If not, you know what will happen? Each worker will cry, and the boss has no idea what work was done. And that is a possible outcome. It looks not so nice, to be honest. What should you do? You have to protect the global variable, and what you can do is, of course, what is the simplest way to protect it? Use a mutex, of course. Thanks. And that's all. You use a mutex to protect cout, and you lock it and you unlock it, and then the access to cout is coordinated, and you are done.
I have one question. Would another possibility be to store the whole message in the string and put it as one operation to cout?
Maybe that's right, but that's not the way I will show you. You are right. But there's a little issue here. That's my first tip. You should not use a mutex directly. What you should use instead of a mutex is any idea? A what? Lockguard, yeah. A lockguard is similar to a shared smart pointer, shared pointer. He protects the mutex. He locks it in the constructor. He unlocks it automatically in the destructor. So it's a kind of array idiom in this environment, resource acquisition is initialization. And that is great, because what will happen if I forget to unlock my mutex? I'm trying for a deadlock. It must not happen, but it can happen. What will happen if an exception occurs? I don't know. It's the same problem. You are in the world of undefined behavior. Have a look here. So I replace this unlock with lock guard, and now you see it here. And the key point is here the lock guard goes out of scope, and the mutex will automatically be unlocked, and you are done. So use a lock guard. So here another problem. I have two threads, T1, T2. One thread invokes a function lock with C2 and C1 and C2. C1 and C2 actually have a mutex, and I do it the same with T2. This time invoking the function lock with C2 and C1. I join it. Have a look what lock will do. It gets the critical data A and B by reference. It uses a lock guard because we learned it. Then he says, get the first mutex. He sleeps only for 1 millisecond. That is enough to make this problem obvious. Then he locks the second mutex, and then he wants to say, get the second mutex. What's wrong with this short example? Bitte? What's the reason for the deadlock? Deadlock is the symptom. You lock two mutex in different directions, so you have a deadlock. What should you do?
Always take them in the same order.
Wait.
You should always take them in the same order.
That's the reason, but there's a more elegant way in C++ 11. Of course, you have to do it in the same order. You have to build a lock hierarchy or a mutex hierarchy or something like that. But there's a more elegant way in C++ 11.
Please raise your hand. I'm coming with a microphone.
Go to the nearer one. Sorry.
I believe it's called lock all, but you pass it multiple mutexes.
Yeah, that's the point. There's a function called stdlock, which you can use to atomically lock more mutex in one step. That's the key. All or once. And the key is stdlock is a so-called variadic template, so you can lock an arbitrary number of mutex in an atomic way. And that, for me, is the most simple way to solve this issue. Have a look here. Here you see the problem. I was too fast. Get first mutex, and you know what I have done here? Control C, because the program is, the application is dead. What I should do is, have a look here. I use in this case not lock guard, I use unique lock, which is similar to a lock guard. It's a lock which protects a mutex, but you can build richer workflows around it. And that's the reason for using unique lock. One workflow which you see here is I defer the locking. That's the key point here. So I have here my mutex, get out the idea, sleep for milliseconds. I take here the second lock, but I don't lock the lock. I don't lock the mutex. That's a little bit crazy in C++ 11. I don't lock the mutex. And now here, that's the key point. Here I invoke lock, and that is the place in which I atomically lock all mutex. Have a look here. The programs works very well. Thread 1 kicks in, first mutex. Thread 2, first mutex, that is the ID of the thread. Then thread 1 gets the second mutex, and now we get both. Then thread 2 gets the second mutex, and he can continue with his work.
Don't you have a race on cout now?
Yeah, of course. You are totally right. But my key point now is cout is only for visualizing something, you know? Actually, it's no problem. You have to live with it. It looks a little bit messy. You're right. In the example before, I had also a race on cout. But my key point was that's only what will look not so nice. The other problem is more serious. A deadlock is more serious in my case. You are right. But do you know the problem? my desktop is too small to show you the full example. Good. So, my singleton. 3 days ago, I have a discussion with Pete Sommerlath, who is one of the creator of the first design pattern books. And nowadays, singleton is not a pattern, it's more an anti-pattern. But forget about that. I will tell you something about the singleton pattern. Do you know what the singleton pattern is about? You create one object in your application. You create it once. It will live for the whole time of your application. And from that point on, you're done. You do it by making the constructor and destructor private. You see it here. Making the copy constructor and copy assignment operator delete. And here you have the static mySingleton instance to which you can refer in the whole lifetime of your application in case the singleton is created. That's all. And you know, we live now in a multi-threading environment, so what should we do? Make that stuff thread safe. That's the key point. And you know, it's so easy. Put only a lock guard around this critical point or this critical region, and that is it. What's the problem with this code? Sorry, wait.
The mutex is created locally?
Sorry?
The mutex is created locally here?
Oh, that's a problem of myself. Forget about it. Make the mutex global. Global. Imagine the mutex is global. Oh. What's the problem? To give you a hint, the code is right in case the mutex is global. But you know, you will access get instance, the method. You have to have an extremely expensive invocation of a lock guard, which makes no sense. You only use instance in a reading way. So you have not to protect anything, but it's extremely expensive. You know what I mean? We program C++, we have to take care of performance. And that's not good from a performance perspective. So, but the world is so easy. What should you do? Sorry, okay.
We could use an atomic bool to check if it's already initialized and if it's...
You are faster than me. The first thing you should think about is create the double-checked locking pattern. I will show it to you. I know the reasons. So what we do, it's extremely straightforward. Instead of this expensive lock guard, hey, you make this test here once more. This one is extremely cheap, and you put it outside. And that is great. That is fast, because that comparison is extremely fast. And only if you get the wrong answer, you make the expensive one. Now we are done. What's the problem with this code? I think, to be honest, that was one of the reasons for Java to getting a memory model. That example.
Where's the race condition on the check of instance?
Yeah. At first, it's called double-checked locking pattern. It's a strange name, but you see, double check once, second, doubled, and locking. And what's the problem? This operation here is not atomic. And that's the problem. What actually happens here is, at first, I allocate memory for my singleton. Then I create my singleton in this memory, and then I refer to instance. So I make this step. 3 steps are actually happening here. But the compiler is able to reorder them, or compiler, processor, caches, forget about it, it doesn't matter. A possible execution order is 1, 3, 2. Not 1, 2, 3, 1, 3, 2. So at first, I allocate memory, then I refer instance to this newly created memory, then a different thread kicks in. And now the thread believes the different one, hey, the object is created, it's fine. But you have a partially initialized object which is not so good. And that is the problem of the double-check logging pattern. So, what should you do?
Get rid of the whole thing by using a function, a static function, and have a static member in there. Because static is now, static initialization is now thread safe.
Yeah, you see, that's the second one. That's the Myers singleton. I think that's the stuff you.
Pretty much. Yeah.
I explain you 2 solutions. The first one, which is a new one, which will come with C++ 11, and the second one, which works also in C++ 89 in a single-threaded environment. So you have not to change something in case you use the right implementation of the singleton pattern. The first one is using call once in once flag. With call once, you can register a function which the compiler or the runtime will guarantee that it will only be invoked once. And to make that happen, you have to use a flag called once flag. Have a look here. That's my getInstance method. I invoke call once. I protect it with this init instance flag, and this function should be invoked only once. And have a look what this function will do. It initializes my instance. So you are done with C++ 11. But you can do it in an extremely elegant way, which is called Myers singleton. And I know now that you know who Scott Myers is. Myers singleton, and that's extremely straightforward. You create a static variable with block scope, curly brackets here, and you know, it is guaranteed says this variable will only create it once, and that's what's new in C++ 11, it will be done in a thread safe way, as you mentioned it. That's nice, but I don't know if the singleton pattern is actually a pattern. I don't know it, but that's not the question. The key point behind here is you have a variable which you will only use in a reading way. So there's no synchronization or coordination take place. But you have only to be sure that it will be initialized in a thread-safe way. So think about these solutions. That's the key idea behind this slides. Now you know thread local data. We have thread local data in C++. Each thread has its own copy of the data. Each thread exclusively owns this data. And it behaves like static data. Will be created at the first usage, and static data, thread local data is bound to the lifetime of the thread. What's the problem with this example? I make it short because I don't know how long I have. There's no problem actually. I don't front run. But you know, my goal was to look around the whole C++ functionality. So you see what actually will happen. You see here, I create thread T1, T2, T3, T4. Each thread invokes the function add thread local. You see here, I have a thread local string s. I add in each thread to s s2. In this case, T1, T2, T3, T4. Now I get the output hello from T4. And you see, the string will not become longer each time. So it must be different instances of a string. And you can also see it here. Here I give out the address of the string, and these addresses are actually different. 3C, 54, 44. So actually each thread has a different instance of this std string. So that was all about thread local. Now, the more advanced stuff. I will talk about condition variables, and I'm not a friend of condition variables, but because a lot of things, you have to keep a lot of things in mind to make a workflow out of condition variables. What's the reason for having condition variables? The key idea is you have two threads, which you want to synchronize. One produces a value, another is waiting for. In case the producer is done, he says notify one or notify all. The producer who is waiting for wakes up. He knows now he can continue. So you have a building mechanism of making something like a producer-consumer workflow. Sounds easy, but actually it's not so easy. So the first one, here you see, extremely easy example. Thread T1, waiting for work. Thread T2, set data ready. Set data ready, say synchronize on a condition variable. You see it here. And set data ready says notify one, because he is done. The waiting thread is waiting for the notification. He do it by using a mutex, which is global to both, you know. And he synchronizes on the mutex. What's wrong with this short example? That's crazy, that example, you know. Yeah.
The condition variable can have a spurious wake up.
Yeah, you know what a spurious wake up is? It's something like you sleep. You get the impression the alarm clock swings, but it's some background noise. It's actually not a notification, it's some background noise. So you wake up, you saw before you get the notification, but it was not a notification. So what you have to do is, in case of condition variables, you have to have a second condition. Have a look here. This is the second condition, bool data ready, equal false. I set it to false. Now my data, set data ready, logguard, uses a mutex to protect data ready, set it to true, and my waiting thread use a predicate in the predicate as a lambda, use a lambda function as a predicate to verify that data ready is actually true. So he waits for the notification and he checks his additional condition. And I think for me that's crazy, to be honest. Spurious wake up. Do you have any idea why I use here curly braces? They are not necessary, to be honest. Only I painted it right, so there must be a reason. Run. Hey, that's a nice job to staying here. But maybe we have a multithreading issue now.
At the closing brace, the lockout goes out of scope, so it unlocks the mutex.
I hope I get it right. It was a little bit difficult to get. I paraphrase it a little bit. The problem is here, I lock the mutex. Here it will automatically be unlocked, and you have to lock a mutex as short as possible. Notify one don't need a mutex, so I unlock the mutex exactly here. And that will be done automatically because I created here I call it artificial block, artificial scope. That do the job for me. I do it often. I don't know if it's nice, but it makes the life more easy for me. And then the next problem in condition variables. Have a look here. That's the main thread. I set data ready. Then I start the thread waiting for work. They do the same like before. Have a look. What can be the problem here? There's a short time delay between setting data ready and waiting for work. And that is, in my sense, terrible.
There might be a situation where you notify the mutex before the other thread starts waiting on it, and then you have a deadlock.
That's the point, you know. I cry go on, but the other part is actually sleeping, not sleeping, he's not running. So one says notify, but the other guy is still not running. The waiting thread has to be awake or running before the notification thread says notify. And that is terrible in my sense, because you have no idea when a thread will actually run. That's out of your control. I don't know how to handle this. Actually, I don't, to be honest, that's only undefined behavior. Actually, I played a lot with it. I made a break of 1 second between, and it worked also, but I'm not sure. I think that's undefined behavior. Have a look here. The key point is at the same time. The waiting thread should wait at the same time the notification thread says notify or something like that. And I think that's a serious problem. Also, I don't like condition variables, but because I don't like it, I show you a more advanced example. I show you a workflow using condition variables. Boss cries to all his workers, prepare your work. Each worker works for a short period of time. Then he shouts back, work prepared, work prepared, work prepared. The boss is waiting for all his workers. Then he says, start your work. Each thread starts once more. He makes his work. And the boss, in case he gets a notification of all of them, says, go home. That's the daily work of the boss and, of course, of the workers. I will create this workflow with condition variables, and afterwards I will do it in a different way. That's the main thread. You can also say that's the boss. Here I create the worker help. I start the help work thread with the worker help. Then the boss says prepare your work. Then I use atomic variable, prepare count store 0. This variable will be increased each time a worker has prepared his work. So it will increase 1, 2, 3, 4. And the boss actually is waiting until this prepared count is equal to 6. Now he knows all workers are done. So he waits for the notification of all of his workers or clients, holding the log prepared mutex, and he waits, wakes up, looks if it's 6, if not, falls back to sleep, and so on, until it's 6. And then the whole story begins. Hey, and then the next notification will take place. The boss says to all his workers, because now he knows all workers are prepared, notify all. So he notifies all his workers. Now you can begin with your work, because your preparation is done. That's the boss, and that's the worker. Oh, that's the worker. The worker gets the name, of course, and that's the actual package the worker will do. He waits for a few milliseconds. Here increases the account. Initially starts with 0, 1, 2, 3, 4, 5. He increases by 1. Then he says work prepared after. He shouts out his preparation time. Then he notifies the boss, hey, I'm done. The boss is actually waiting for this notification. Then here, he waits for the boss until the boss will send him the message, start your work. And that is here, start work. As before, I used here curly braces, because in case I forget to do it, what I in the first place actually forgot, this start work mutex will be locked forever. So only one thread, one worker can proceed. So you have to have a lot of think about the workflow to make it right. And then the whole step begins once more. He sleeps. He increases done count. Then he waits for the notification. Then he sends his notification, hey, I'm done with my work. And then he waits for the instruction of the boss, go home. That's the workflow, the boss and the workers. And you know what? I hate condition. No, that's too much. I don't like condition variables. To make that happen, you can use promise and futures, or to say differently, use task. Sorry, that was, you want to ask a question? There's actually no problem, as far as I know.
This code, I think this code has a deadlock problem, because...
Where?
Can you go back one slide first, for the boss thread?
Now we have another reason maybe to use the task. Yes, go on.
Yeah. You wait, it locks the prepared unique, prepared mutex, and then it waits for the prepared count to go to 6.
Yo.
And then it does the same later with the wait for the done count to go to 6, but I think can you go forward one slide?
This is not possible. This is in the wrong direction. One additional remark: prepare count and done count are atomic variables. Only to make
no, the problem is not the access to the count variable, but the problem is that the worker holds no mutex when it does the worker to boss condition variable notify 1, and that means.
Where's the mutex missing? Give me a hint.
Before the last opening curly brace.
Here?
No, before the last one. After
here? No, here I have a mutex, a lock. You see? Here I have a lock.
No. It's not about the lock. It's about the missing lock. It calls worker to boss condition variable dot notify 1.
Sorry, I don't get it.
Further down, further down. A bit more. Yes, exactly. This line.
And what's here the point?
The worker does not have a mutex, and that's why it cannot know that the boss is already waiting. In this case, you make a sleep, so it's very likely that the boss has gotten around to its wait call. But if you take out the sleep, for instance, you may notice sometimes a deadlock because the boss is not waiting. So it's possible that the boss has not gone around to wait for the worker to boss condition variable, and all the workers, however, are already done and make the notify, and then the boss calls the wait, and nothing happens because the notifies are lost. They are stateless.
Sorry, I don't say that you are right or wrong. I only say that it's too much for me now. We can discuss later. Is it okay?
Yeah, I think there would be a fix. So the fix would be to make the worker to boss condition variable notify 1 to wrap it with a lock for the worker done mutex.
But the key we refer to it later. One additional point, I played a lot with this example because I shoot me 5 times in my own food, you know? I just discussed it with mailing groups or something like that, and maybe you are right, I don't know it, but the key point is I don't want to use it. So we should go further. As you see here, I have a task, and tasks are this special promise future synchronization primitives, or not primitives, promise future endpoints of a data channel, which can help you to produce a value in the future, which you will get by a future. And the key idea is a promise will give you a value. This can not only be a value, this can also be an exception or only a notification to, in this case, to notify a waiting thread that he should continue with his work. Though you see, there's also a notification involved. And I show you an example for promise and futures. And then you will see that is a lot more easy to handle such workflows with promise and futures, because You have not to take care of mutex, of locks, of atomic variables, of spurious wake-ups, and you know, this stuff. So, promise, I called it promise and future, but under the hood, these are, I call it tasks. These are promise and future. Have a look here. That is a promise. Async is a function. You can look at it as an asynchronous invocation of a function. This function will evaluate or execute a lambda function. And this function will give you back in future. This equal signs here creates a data channel between the async and the future. And then the future can ask for the value. In this case, he gets 2011. This is be done implicitly. I can also do it explicitly by using std future and std promise. Here I have a promise. Here I create my future from the promise. And here I have my future. Now I have two endpoints of a communication. The promise and the future. Both are connected by a channel. And what I have now to do, maybe move the promise in a different thread or something like that. I have two endpoints of communication. Now I have to handle it. Then here I create a thread, some thread. I give the thread a few variables. At first I give the thread the thing the thread has to do. Then I give the thread the promise and the two variables a and b. Now have a look at the function sum. The function sum will take a promise by a value reference and the arguments x and y, 1011. And the promise will set the value, and the value is 2000 plus 11, 2011. Now the future afterwards can ask for the value, and he gets the answer, 2011. So promise gives you a value, future asks for the value, both are connected by a channel. The promise will send the value in the channel, the future will take it out. It cannot only be a value, it can also be an exception and, you know, a notification. And by this notification, you can use notifications to simulate condition variables, and that's my key point. Only to remind you, that's the workflow I want to achieve. So that's the boss. Now it looks a little bit different. What you have to do is to think about, we have a start work prom and a go home prom. This promise is used, the boss used this promise, start work home, to shout to all his worker, start your work, to shout to all his worker, go home. These are two data channels. Each worker also needs two data channels. One to say to the boss, I'm done with my preparation. One to say to the boss, I'm done with my work. And that's what I described here in a few words. I will show you in code. Here, start word prom, get future. I get the future out of the promise. That's a shared future, you know, because in case the boss says start work, all workers has to hear it. It's also for go home. Then here I only show you help. That's help. Help needs two promises. One to say to the boss, I'm prepared. One to say to the boss, I'm done. So have a look here. I use this promise to get the future. That's only a simple future, no shared future. And now you see here, that's the actual, that's the thread, help work. He gets his work package, help, and he gets two promise transferred, no, to say it exactly, moved to help, because a promise cannot be copied, can only be moved. And he gets the future. He used help prepared and help done to say to the boss, I'm prepared, I'm done. He used start work future and go home future to ask the boss, wait for the notification. And that now the workflow starts. Here the boss waits for all his workers, you see it, wait for help prepared, wait for help prepared, wait, terrible. Wait for Scott prepared wait and the other 4 guys. Then, in case he gets the notification of all his workers, he says to all his workers set value, and that is similar to condition variable. You say notify all, and here you say set value. That's a notification, because that notification will go to all his workers. It's a shared future. All workers get the signal, start work. And now the same step begins once more. That's not different. And now have a look at the worker. Here he gets the promise, 2 promises by R-value reference, and he gets the shared future. These are the data channels, 4 data channels, 1 for waiting, 1 for sending a signal. Here, arbitrary amount of time. Here set the value. That prepared work notifies the boss that he's done with his preparation. Now he's waiting for the notification of the boss, because the boss has to say, start your work. And then now, on here, the same. Honestly, that is not so easy to get, but my key point is no mutex, no lock, no spurious wake-ups, no atomic variable. It's a lot easier. So, the hard work is done. Now we go to more interesting details. I will not go into the details. I will only show you a little bit of code, and I will talk a little bit about, only a little bit about the memory model. We will play a little bit of code, and we synchronize it in a wrong and a right way. We will see what will happen, and I have to wait for the answers. The memory model deals, in my sense, with 3 main topics. The first topic, what is an atomic operation? Second topic, partial ordering for operation. That means which partial ordering for the operation is guaranteed on one thread. What can be reordered, what not. Third one, when is an effect on one thread visible to a different thread? When is this A equal to 1 visible on the thread 2? These are the concerns of the multi-threading memory model. So, I use each time this small example, and we play a little bit of it. And you know, I can set what is true, what is false. So I wait. Have a look here. I have a thread T1. He's writing something. You see, X and Y. And a thread T2 who is reading something, Y and X, in the different order. What are possible outcomes? X and Y are not atomic. What are possible outcomes? So, sorry? All of them. He says all of them. Is he right or is he not right? Right. One additional remark. Yes, all of them and a lot more. It's undefined. I don't know it. So that's bad. What should we do? One tip: we should begin with the with the simple ones. If you have no idea, in this case, only lose a lock guard. I protect it, you know, and I do it in an extremely strong way. What are now the possible outcomes?
First or last?
First is 0, 0. Last is... Oh, sorry. I have to say it's wrong because we have to discuss, but you are right. First and last. What should we do now? I told you we talk about atomic variables. So, I make X and Y atomic. What are now the possible outcomes? I like it. We can make it in a different way. What is not possible? Sorry? Why? In my sense, not.
No, it's not possible. That's what you were asking.
No. My question is, which cross can I set here? Sorry? No. No. Second one means x 0, y 11. Exactly. That's the answer. But now the problem will start. We have to reason about it. That's extremely simple, you know. How should they do it? Yeah. The default for having atomic variable is sequential consistency. Oh, yes, that's terrible. I should speak German. Sorry. But to be honest, I cannot speak it in German also. It's a problem of my tongue. So, sequential consistency is the key idea behind it. And what sequential consistency will guarantee is you have how can I say, a global order of all instruction. And that's the key here. That means, in case you read yload, and you know y store is set, x store has to be happened before. So there must be a global order, and that is great. That is our intuition, you know. That is the easy one, you know. You know it, of course. So all outcomes are possible except of that one. I have to do it in a different way. Now, we have to be faster, you know. Now, maybe I have to ask it before. Now I make acquire-release semantic here. So, I acquire here. A load is actually an acquire operation. A store is actually a release operation. So it's enough to say acquire and release. Relaxed is more, yeah, of course, relaxed. No guarantees. What is a possible outcome here? I think that's relatively simple. The answer is more challenging. We are nearly done.
Any one of those four is a possible outcome?
Maybe. Your answer is correct in 75%.
I think the answer is the same as before, so
100%. Why? That's the interesting question is why. You know, this y load synchronized with this y store. These are the same variables. So you have between this both a synchronized with relationship. You have here between this x store and y store a happens before relationship. And you have also between this y load and this x load a happens before relationship. Now you apply transitivity and you know this x store must happen before this x load and then you are done. So between the threads you have a synchronized with relationship. And in the thread, actually, you have a happens before relationship. And now the whole is only taking the pieces together. Now, the last slide. Now, what can I improve in this program? Before I go, we have 2 slides are still missing. To be honest, memory order relaxed is not necessary. It's enough to make int a normal int, non-atomic. Because, what's the reason? This release operation will guarantee that all what was happened before actually happened before. So you can use atomic variables to synchronize non-atomic variables. That's the key idea. So you have not to use atomic variable here. That is well defined. You get the same output like before.
I have a question. Is it guaranteed that the store of 2000... Thank you. Is it guaranteed in this case that the storing of 2000 is propagated like from one CPU cache to the next one? So when I read it, that I actually see the 2000?
It's guaranteed that this happens before this one. And the reason is this store. Yeah, I know your question. As far as I know, that is guaranteed. That's the key point. The key point is not that it's guaranteed. The key point is that you can use atomic variables to synchronize non-atomic variables, because we have here this synchronize with relationship and also happens before relationship. 2 questions from the back.
Just a comment, here you have a data race, so in order to avoid it, you need actually to wait until y loads the new value of y. So you need a while loop.
Why should I wait for y load? Load is y is an atomic variable? Sorry, I don't get it.
So the first thread so the writing thread can write to x, the second thread can execute the load, can execute x, and can reach from x. There will be no happens before dependency from store x to reach from x, and then you will get a data race because you have a store and you have a load which is not synchronized with it.
Actually, I'm relatively sure that it works because I wrote the papers from Sutter, but we have to discuss it later.
There is a data race here for sure.
Yeah, so actually what this guy was saying is you cannot be sure to see the value of x if you don't load the value of 11 from y.
I don't get your last half of the sentence.
So you only get, the store only synchronizes with the load if the load actually reads the value that was written to by the store.
But,
so if you read 11 from y, then you are fine, then you have synchronization. But if you don't, if you maybe still read 0, then there's no synchronization at all, and that's the data race the other one was just mentioning here. So as long as you read 11, you are fine, you don't have a data race, but if you still read 0, if you run the reading thread, then you have a data race, because there's no synchronization unless you actually read back the value that was written.
We should, okay. Of course, yeah, okay. You see, there's a lot of discussion. Now to my last slide, which makes my life extremely easy. Now we have relaxed. What can happen? 100%. All values. Also the way, what was it, x equal to 0 and y equal to 11. That's also possible. What's the difference between this one and having non-atomic variable here?
No undefined behavior.
Yeah, the reason is the only guarantee you have, or the essential guarantee you have in this case, is the load and the store are atomic. And that's, maybe it's enough what you want. So that was it.